Okay, if you have a question about the homework that was due today, in these problems right here, 1 to 22 and 33 to 36, those are the ones that you should have known how to do from what you saw on the video or what you heard in class. And so if you have a question about one of those, don't mind going over it. Anybody with a question? Okay. Number 6, okay. Is it 6 on where it's got X as the cosine and Y as the sine? Okay. All right, excuse me. All right. On this, it says complete the table for the parametric equations and plot the corresponding points. Okay, so in 6, when it says X equals the cosine of t, Y equals the sine of t, and when they give us the values here, the different t values, they go 0, pi over 2, pi, 3 pi over 2, let's see, 3 pi over 2, and 2 pi. All right, and here's X and here's Y. All right, Katie, you're going to see in a second. All this is unit circle, right? Because right here, if I put a 0 into for cosine, then that's 1. The cosine at pi over 2 is 0. The cosine at pi is -1. The cosine at 3 pi over 2 is 0. The cosine at 2 pi is 1. So it's just those 5 key points. All right, and then down here, we get the same kind of thing. Okay, so right here on this will be 0. This will be 1. This will be 0. This will be -1. This will be 0. Okay, now, if we have to graph this, it says in the B part, plot the corresponding points, all right, then that's the part about this that becomes interesting. All right, so we're going to plot 1, 0. All right, let's see. Yeah, I put those numbers on there like an idiot. I'm sorry. Let me redo. All right, because this is X and this is Y, and so I want the point 1, 0. All right, and then this one I'm gonna get the point 0, 1. On this one I'm gonna get the point -1, 0. On this one I'm gonna get 0, -1, and then I'm gonna be back to the same place here. Now, on that, do you get the idea that we could very well be going around in a circle, if we had other values in there? And that's what actually is happening in that problem. Okay, let me show you one other thing about this. This is just sort of for everybody's benefit. In class, we talked about doing these with the calculator. All right, now, again, for people that were absent and whether you listened or did not listen to the thing, anytime you've got sines or cosines and you're going to graph, you want to be in radian mode as opposed to degree mode. And then when you have the x's and y's both given, we're going to be in parametric mode. Okay, and when we go to parametric mode here, then we can just put in cosine of x. I didn't get it up to the top, my fault. Got that in the wrong place. All right, put cosine of x here, which becomes cosine of t, and then this one becomes sine of t, and that's what that was to start with. Okay, now if we go second and then window, which is table set, we can come down here to the independent variable and go over to ask. Well, I'm sorry, we don't need to do that on this one, my fault. Let me go back up here. Because our numbers go up 0, pi over 2, pi, etc., we can start the table at 0 and go up by pi divided by 2. All right? And then, if I press enter, I'm going to go second table, and it has all those values. Now, the hard part about that is you're going to realize this is 0, this is pi over 2, this is pi, this is 3 pi over 2, this is 2 pi. Because it doesn't leave that in that t column, but it gives you all your values here. Okay. All right. Anything else? All right, number 36. Okay, everybody look at 33 to 36. If you don't have your book open, would you open it to page 530 for just a minute? 33 to 36 sort of go together, and it says it refers to the graph of the parametric equations x equals 2 minus the absolute value of t, y equals t minus 0.5, and we go on the interval from -3 to 3. All right, we need to put that in the calculator here. So, all right, we're on page 530, and we're right above problem 33 where it has the equations. So we want 2 minus this absolute value of t, and then we want t minus 0.5. I believe that's right. Yes. All right, now we need to go to window so we can put in our t interval. So we're going to go -3 to 3. All right, and then we're going to put the t step as 0.1. All right, and then we'll make these for right now, just so we can see something that's good. For this minimum, I'm going to make it -9.4 and then 9.44 x max. And then for the x scale, -1, and then y min is -6.2, y max is 6.2, and the y scale is 1. Now, one word about this for everybody is all this is these are the coordinates for zoom 4, but everything's doubled, okay? But it makes a unit on x the same as a unit on y, and so if something's supposed to be a right angle or something's supposed to be circular, it will look that way in the graph. All right, now, what's key here is that we put in that -3 to 3 for the step. So now, if we look at this, you can see the graph that they got. All right, now they want to know in 36 what values of t graph into points in the fourth quadrant. And so all we do here is we just use the trace button. All right, we can just go over here until we're looking at the x number here. All right, and when the x gets to be 0, all right, right there, all right, where this is always in front. Okay, then for 36, since we're doing fourth quadrant, the t value here is -2, so we're going to go -2 is less than. All right, now, notice that point right there is not in the fourth quadrant. It's on the line between the two quadrants, and that's why this is a less than sign instead of a less than or equal to sign. All right, now we're going to go is less than t. All right, and then all we're going to do is we're just going to keep toggling to the right until we get up to where the y coordinate is 0, because that's when it'll come out and go into the first quadrant. So I'm just looking at the y's, and right there the y is 0, and this t value is 0.5. Okay, now I need a less than sign here for the same reason I needed less than as opposed to less than or equal to the other time, because the points that are on the x and y axis are not in a quadrant. Okay, go back to window for just a minute. Is your t-step 0.1? All right, let me see what's going on. Oh, here's what it is. I didn't notice until it was here right there. You got in instead of 0.5, 0.05. And that's the difference. Okay. All right. Let's get into the lesson today. The lesson today is going to, the first thing we're going to do is at the end of the video last time, or if you were in class, at the end of class, we talked about graphing a segment and graphing a line. And so I put that homework into the part that you're going to do tonight. All right, and I'm just going to copy back up the stuff that was there and just do a little quick thing about it. All right. I had told you, do not try to do it the way they do it in the book unless you understand vectors really, really well, because it's hard to come up with their equation. All right, something that I don't know if you picked up from the video, if you missed class, is that for every parametric graph that you can get, there can be a number of equations for it. Sometimes, quite often, as a matter of fact, infinitely many.
Where are you?
All right, I am in the new packet that I have not handed out to you yet. Sorry about that. I was feeling the pinch from what I sent to me in the time crunch to get done all the things that we need to get done. And didn't do my job very well. Okay, so on this part right here, last time in class, we had come up with this equation. We had said the equation for x is going to be x sub 1 plus delta x times t, and the equation for y is going to be y sub 1 plus delta y times t. All right, and rather than me say all that again, if you need to hear it, I'm just going to tell you, go back close to the end of the video, and it will talk about this. All right, now the x1, y1 that it's talking about here is a point on the graph that you're given, and you want it to be the point farthest left, okay? Now, when you're given 2 points, let's say we were given a point negative 3, 4, and we were given a point 6, negative 2. How can you tell which one of those is farthest left?
Negative 3, 4.
All right, negative 3, 4, because it's the one with the smaller x coordinate, right? Okay, now, if you happen not to use the point that's farthest left, you can get an equation for the same line, all right? But if you're going to get the equation for the segment, it causes your t interval to change from what it would otherwise. Okay, so now, right here, this is the general formula. If you apply this formula, if you want to get a segment, all right, whose endpoints are these 2 points, are the 2 given points. So for an example, we'll have these. So if we want to get a segment, normally we will need to let t go between 0 and 1 for this. All right, if we want to get a line, then it's the same thing, except t goes between negative infinity and infinity. Okay, now I'm going to do a real quick, just doing this problem. There was one like it again that was on the tape, but the first thing that you need to do down here, the delta x and the delta y, remember that the slope is the change of y over the change of x. All right, so it's y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Okay, so right here, if I want to get the slope here, I'm going to take the point farthest right here, and so I'm going to do its y coordinate, so negative 2 minus 4, and then I'm going to go 6 minus a minus 3, which will make that a plus 3. All right, and I'm going to get a slope here of negative 1. Okay, I'll tell you what, if you get a slope like negative 1, it makes the problem somewhat easier. So let me just change a number right here. Let's make this, say, negative 5. Okay? All right, therefore, right here, if I make this negative 5, like that, we won't get negative 1. Okay? Now, wait a minute. Let me go back to what I had, because then I shouldn't be getting it. My fault. It's not too good when you can't subtract and get the right value here. Okay, so this is, I'm sorry, it's negative 6 over 9, right? Okay, now, I'm going to suggest to you here that if you want to keep that idea of the 0 less than t less than 1, that you not reduce the fraction. Okay, so we're going to look at that just like this. Okay, now, right here, that top part is delta y, and that bottom part there is delta x. So if I want to write an equation for the segment that goes from here to there, I'm going to write in red because I'm running out of room and I want you to be able to see everything without it being erased. All right, I'm going to take the x coordinate that's here, so negative 3, and then I'm going to put the delta x. Now, delta x is on the bottom, and so this will be 9t. All right, and then for y, I'm going to put the 4, and then I'm going to put plus, and I'm going to get the delta y, so that'll turn that into a negative 6t like that. Okay, take your calculator out for a second. All right, if we put these two equations in, negative 3 plus 9t and 4 minus 6t, okay, go to window, and for t min put 0, and for t max put 1 for right now. All right, and now if we hit the graph button, all right, now put on trace. Now the reason for putting on trace is it shows you a bunch of stuff that's good. Do you see that when t is 0, I am getting that leftmost point? All right, and now I'm just going to toggle to the right so you can see what's going on here. When t is 1, we get the other endpoint, which was 6, negative 2. And so that's how I came up with this interval right here. Now, if you reduce, for example, if you make this to negative 2/3 right here, so that this becomes a 3, and this becomes a negative 2, what would we need to change the t value to this time to get that same segment?
Are you asking me?
Yes, you're the only will in the room, right?
I'm sorry, I didn't hear it. What?
Okay, the reason I asked was I thought you were sort of tuned out to start with.
Yeah, it was.
Okay. All right, let me repeat the question for you. Okay. I had told you earlier to not reduce this, and then you would always get this 0 and 1 concept here. And for a lot of students, that's sort of important. All right. If we reduce it here, we can still get the same segment, but we won't get it in the interval 0 to 1. Now, one of the good things about doing anything on a graphing calculator is you can experiment and you can very quickly change things you need to change. So go to y equals everybody and just make these changes. Change the 9 right there to a 3, and then change this negative 6 here to being negative 2, like that. Okay, now, the first thing I'm going to do is I'm just going to have us graph it the way it is. All right, now if I graph it, do you see it looks like it started about the same place it did start, but it stopped short, right? Now, if you put the trace button on, trace shows you a lot. When it's 0, you get negative 3, 4, which was this point. Now, this makes sense if you'll just think about it. If you put a 0 in these two places, it wipes out that side, so you just get what's here, right? Does that make sense? Okay, now, if I reduced this by a factor of 3, what number would I need? Let's see, I didn't reduce it by a factor of 3. I reduced it by, yes, I did too. I reduced it by a factor of 3. So instead of going from 0 to 1, I would need to go 3 times as far to get it to be the same thing, I think. So right here, go to window, and you can change this to a 3. All right. Now, if I graph it, all right, now I'm going to go second trace this time. Now, first of all, for those of you who haven't seen the video, when you're in parametric mode, you can't do max, min, intersect, 0, and a bunch of those functions, but you can still do value. And these other things here are things that you do in calculus, okay? So right here, if we just put this in, let me put in 0 to start with, and you can see that we get that point negative 3, 4. Now, if I put in the number 3 and press enter, you'll see I get the 6, negative 2. All right? Now, here's the point I want to make, because I don't want to stay on this the whole morning, is that when you first do the slope formula, if you'll just take the numbers as they are and not reduce them, and the top one is delta y, the bottom one is delta x, and put them in the appropriate place here, you can always wind up going from 0 to 1. Okay? Now, on that part, when I told you that x1 and y1 was the point farthest left, if you use the other point instead, all right, to go here, then instead of going from 0 to 1, you have to go from negative 1 to 0 to get it to work. Now, you can fool around with your calculator to get that to happen, but if you just want to learn, okay, Mr. Andrews is going to make me graph a line on the test, Mr. Andrews is going to make me graph a segment on the test, the easiest way to do it is to just learn that fact, okay? All right, and I think it's a good time to repeat, to get any one thing in parametric mode, there's usually infinitely many different ways to get the thing to happen. There's 4 easy ways to get what we just did here to happen, all right? But you just want to learn one. You don't want to learn all of them, because this is just one thing out of many that we can do. Okay, now, all right, notice that the heading up here is the difference between graphing a segment and graphing a line. All right, if we have a beginning point and an ending point to our t interval, then we will have a beginning point and an ending point to our graph. Okay, if we begin at negative infinity and go all the way to positive infinity, then we will not have an ending point. And so if we have something that is a segment but it keeps expanding, it would be a line if it goes from negative infinity to infinity. Okay, now last point. Go to window one more time. If we want to graph a line on our paper and make it look like a line, generally speaking, you want to go negative 10 to 10 for the t, and that usually will take the graph all the way across your paper. All right? It's sort of like, when we graph in function mode and we're going to graph a parabola and we know the domain is negative infinity to infinity, we just go negative 10 to 10 because usually the important stuff happens with values close to 0. Same principle as that. Okay, now, let me just see if I've either made the point clearer or clouded. All right? Whether you're graphing a segment or a line, you're going to use this form to get what you want. The difference is, if you do it the way that's described, your domain, your t interval for the segment is going to be 0 to 1, and for the line it's going to be negative infinity to infinity. Okay? There's some problems. I want to say it's 26 to 29, but it might be like 27 to 30 where you have to do that in the homework. Okay. Now, the rest of the day, the topic changes from what that was, and it really becomes a sort of interesting topic. But we're going to talk about simulating different kinds of motion. All right? And the first thing that we're going to do is we're going to simulate horizontal motion, and we're going to do this by having 2 people run a race on the calculator. All right? So now, anytime that you simulate horizontal motion, there's 2 things that you need to be conscious of. One is setting the window, and then I put down here issues with the y values, and let's take a look at where that could come into being. All right, so right here, example 7 on page 526. Would you look there for just a second? All right, now, this example is the one that's going to give us the idea about the issues with the y values. Okay, so go to y equals and clear out the 2 things that we have here. All right, and then on page 526, example 7 says this. It says, Gary walks along a horizontal line, think of it as a number line, with the coordinate of his position in meters given by the equation S equals negative 0.1 and then that other equation where 0 less than or equal to t less than or equal to 12. Now it says, use parametric equations and a grapher to simulate his motion and estimate the times when Gary changes direction. Okay? Now, when we do this, if we're going to simulate horizontal motion, all right, the y coordinate on a horizontal line is always the same. So when we do this, we can come up here and for the y coordinate, we can just put in any number we want. I'd like for you to put in 2. You don't ever want to put in 0 because if you have your axis in, then the activity is taking place on the axis and we probably can't see it. Okay? All right, so I would suggest a 2. All right, and now go up to the top one, and I want you to copy in the equation out of the text there. And I'm going to do the same thing here. So it's negative 0.1 and then t cubed. All right, now do the little right arrow thing to get it back down where it's supposed to be. All right, minus 20 t squared plus 110 t minus 85. Okay, now before we do anything with this, I need to tell you that they are trying to get something so that they can show a particular point. Normally when we have an equation for somebody walking back and forth on a line, it's either going to be a quadratic or a cubic like this, but it doesn't usually have that little negative 0.01 out there just to make sure certain things happen. Okay, now go to window before you graph. If you were not here last time, one of the key things to this is never graph without considering the window you're going to graph it in first. Okay, now they tell us a t interval here, all right, and they want us to go from 0 to 12. And our rule of thumb is this. If there's a trig function in it, the t-step is pi divided by 24. That's a number you want to remember if you weren't here. All right? And if there's not one, the t-step should be 0.1. Okay? Now, for this particular problem, I want us to use negative 10 to 10 here. All right? And I want us to leave the other one. Now, the reason I need to go negative 10 to 10 is this graph gets very close to the edge of the graph. And I don't think at the negative 9.4 we would see the end of the movement. Okay? Now, don't hit your graph button yet. Let me have you see the thing up here, because what we're going to do is we're going to do this problem 2 or 3 times with the idea of how can we better see the motion. Okay? Now, all right, so here's the first part. Which direction was he going to start with? He was going to the left, right? Could you ever tell if he changed direction? No, because everything was happening one on top of the other, right? Okay, so let's go back to y equals, and let's do something that'll help us with this. All right, would you toggle to the left till you get to where this is? And then would you press enter until you get to where it has this look, where it looks like it's got the little ball connected to the thing. Well, I'll tell you what, let's go one past that to start with. Let's go to this one. Now I want to come back over. All right, now we hit the graph button. Now watch what happens. We can see him move. We can see him slow down. Man, he got close to the edge. But then we see him speed up back in the other direction. And it looks like he's slowing down again. And then all of a sudden he's going back to the left, and it looks like he might be speeding up. And the next thing you know, he's gone. Okay? Now, so do you see that the advantage of that one is we could actually tell there were changes of direction. We could not tell that to start with. Okay? Now, let me have you go back and go back over to where we were. And this time, I want you to put get the one that has the connected one here. All right? Out of all of these, this is the thing that's most beneficial most of the time for us. Okay? Now, if we do the graph here, you can see him going to the left. You can see him slowing down. Now, you're just going to see him going back across the same path. And you, once again, you'll see him speed up to the left and he goes away. All right. Now, they ask us in the problem to try to find where he changed direction. Okay? Now, one way to do that is to use the trace key. All right? Now, if you just put the trace key on, the first thing I want you to notice is that if you go right arrow here, now again, I'm talking with the understanding that some of you may not have seen the video. If you were in class last time, we went over what the trace key does. All right? But on the trace key, if you go right arrow here, what it does is it increases the t value. It does not mean the cursor goes to the right. All right? The cursor goes just in the direction of motion. Okay? Now, because we're moving to the left, we want to see when we get farthest to the left. So just keep going here, and as long as this x value keeps getting smaller, I think you can see it's getting smaller, then we want to keep going. Okay, now it's -8 something. Now it's -9 something. All right, now go slowly from here, but you can find that he's going to get to at a place that's pretty far to the left, and then you'll realize the next one is bigger, and so you can tell when he changes direction. All right, so right there, this is farther to the left than -9.2. This is farther to the left. Still farther, still farther, still farther, still farther, still farther, still farther, still farther. Not as far, right? Because it went back to a 0. All right. Now, this is at t = 4. So somewhere in there between t = 3.9 and 3.4, the particle changes direction, or the person doing the walking changes direction. How many of you are in a physics class? Okay, all right. Now, if you're in a physics class, do y'all do position, velocity, acceleration? Okay, and so we could describe the guy at the beginning, his velocity was negative, right? Because he was moving in the negative direction. And then between 3.9 and 4, then his velocity changed to the positive direction. And in physics, you always are looking for the place where the velocity is 0, right? So that you can tell the change of direction. Okay, now, next year in calculus, y'all are not in a calculus-based physics class because you're in this math class, all right? But next year, are you in the one that Mr. Hasselberg teaches? Okay, all right, in the one that Mr. Runge teaches, is it called Physics C? Is that the one he teaches? All right, you use derivatives to tell where you change direction. Does anybody know right off, because some of you might, does anybody know what the derivative of position is? Okay, I won't try to teach it from that point of view because nobody's saying they do. But I want to just say this for informational purposes. In calculus, you will learn that velocity is the derivative of position. So once you know what the derivative of a function is, the way you get the equation for velocity is you take the derivative of the equation for position. And then acceleration is the derivative of velocity. And what we're doing here is we're trying to do physics for people who have not had calculus and how you can try to determine where the change of direction is. So what we just did there is a way you could try to determine that. How do y'all do that in Mr. Hasselberg's class?
Velocity and displacement and all that?
Yes. How do you tell when the velocity changes? Does he just give you a velocity equation and you have to solve for where it's equal to 0?
Sometimes they'll give you like an initial velocity or a final velocity, and there's like certain equations you can plug it into.
Okay.
Find because we did this like first semester, like in our earliest chapter, where we did it with like velocities and like where like placement and accelerations
Right.
and stuff.
All right. I am assuming, not having been in his class, that he's giving you the formula for what the derivative would be, so you can get that. He's just not calling it a derivative. He's just saying that's how you get it. That's a guess because that's how it connects. Now, those of you who take calculus next year and take the physics C class, because if you're if you're going to be into sort of math and science in college, that where it's applied, be an engineer type thing, those are two good courses to take while you're in high school. Okay, all right, because most of the people who are going to be your competition when you get to college are going to take those things in high school as well. Okay, so anyway, right here, we get that change of direction, and that's all we're interested in this one. Now, there's another change of direction that you could get if you go out this way, but compared to the other things I want us to do today, I don't want to spend more time for that. So let me put this down for a second. All right, and now, okay, come on. I'll just leave that there for a minute because it ungroups itself. Would you copy this one? I'll tell you what, instead of you copying that, let me just explain it to you. All right, you don't need to take the time. All right, we'll just go to a blank thing here. All right, we're going to have some fun. We're going to have a race. All right, the Daytona 500 was Sunday, right? Okay, so we're going to have our version of the Daytona 500. All right, so now, the big deal to us is we have to set up what our race is. Now, when I tell you that ours is a version of the Daytona 500, they go around in a circle. All right, I can show you how to make them in an oval. I can show you how to make it go around in an oval sometime, but that's not where we need to start. We need to start with two cars going in a straight line. All right, but we're going to have them race for 500 miles just because that'll make it interesting. Now, we have to set up the racetrack. So we need to have 500 on the right, and we need to have 0 here on the left. Okay? Now, we're going to have them go horizontally. So our two racers are going to go like that. All right? Now, who would like to race here? Thomas,
I'll race.
You're a guy that would have a little bit of speed here. Okay, so now, for X1, what we have to do here is basically put in a velocity equation for Thomas. All right? All right. Now, I'm going to say that Thomas, when he's racing, is going to go 160 miles per hour. All right, and it's T. Now, what's going to be interesting here where it's not really true to fact, Thomas is getting in the car, he's sitting at the starting line, and instantly he's going 160 miles an hour. If that really happened, his neck would be at the starting line and his body would be out ahead. There'd be a big jerk there. But anyway, we're going to assume that we'll assume he started back here, and when he gets to here, he hit 160 miles an hour. It's going to keep it up. Okay, now we got to give him a lane to run on, so we'll let Thomas, that's called Y1, we'll let him run on lane 2. Who would like to race against Thomas? All right, Ellen's going to race, all right? Now, what I have to decide here is, are we going to be nice to ladies to start with or not? All right, I'm going to assume to start with that Ellen is more like Dana Kilpatrick, and she cannot race quite as fast as some of the best racers. And so I'm going to make her go at 150 miles an hour, and I'm going to put her, 150 miles, that's a fast woman right there, if you're doing that. All right, and I'm going to put her on lane 4, okay? Now, who's going to win this race? All right, Thomas is, okay? All right, now, we just need to see the race to start with, and then after we see the race, then Ellen, I'm going to have mercy on you, and we're going to make it where you got a shot. Okay, now, the first thing I want us to do is I want us to clear what we've got in here. Let's see, so clear. All right, now, we're going to put Thomas in first, so we're going to go 160T. Now, do you remember the old 8th grade formula, distance equals rate times time? That's all we're putting in here, where x is the distance he's traveled so far as a function of time. Okay, so 160T. All right, and we're going to put him on 2. All right, and then down here, we're going to get Ellen going 150 miles an hour, and we're going to put her on lane 4, so she'll be on the top lane. Now, in both of these, if we'll go back up to this first one, the race looks better if you have that connected circle there. Okay, so we're going to do that. Now we're going to come down. We're going to do the same thing for Ellen here. All right. Now, we got to set up the racetrack because this is the big deal. All right. Now, we'll come back and do the T step in just a minute, or the T window. But let's go here. Our X men needs to be the farthest to the left. okay, that we're going to be. So that's going to be at 0. And our X max needs to be down the track at the end, so we're going to go 550 there. All right, and we'll put in here, I'm sorry, not 550, 500, my fault. All right, 500. Okay, and we'll put a scale on this thing of 100 so you can get an idea when they've gone 100 miles. All right, now, this negative 6.2 and 6.2 is going to be, well, let's see. Let's do this. Let's make it -1 right there and 7 for X max. Okay, now go back up to the top. All right, now, if they're traveling at least 150 miles an hour, it's going to take them less than 4 hours to go the whole distance, right? So this race is going to be over pretty quick. All right, so right here, let's just put a 4 here. And what will happen is they'll run off the edge of our screen. We just won't see it. But whoever gets there first, obviously, is the winner. Okay, now watch it here and then do it on yours. That way you get 2 looks at it. All right, so here we go. They're off. Whoa, just a minute. Major mistake. All right, Ellen had engine problems right there. All right, she got them fixed and she's now trying to catch up. But that's not her fault. That's mine. All right, now the other thing I forgot to tell you is this: go to mode. All right, we need to be, instead of sequential mode where one of them races after the other. It's not much fun to do that. That's time trials. And so we're going to make them run simultaneous. All right, now here we go. All right, and they're off. And Thomas is at the bottom, and he's got a slight lead. Ellen's working hard to catch up, but nobody's stopping for gas. It's amazing. They went 500 miles, no pit stops, but Thomas wins. Okay? All right, now, if we want to give Ellen a chance, we've got 2 things we can do. Or there may be more, but one of the things we can do is we could speed her car up. But everybody understands if we do that, she wins, right? The other thing we could do is we could give her a head start. All right, so let's give her a head start. So let's go down here where Ellen's at. All right, and let's go out to the end of this thing, and let's put a plus, okay, and let's put a 25 here. All right, now we're giving her a 25-mile head start, right? So when we see this in a minute, instead of her starting at the beginning, she's going to start out this way a little bit. All right? Is that going to be enough for her to win? All right, no. How much does she need, girls? If you want to make the girl win, how much does she need?
At least 50.
All right, at least 50? All right, I'll tell you what, we'll give her 50. Okay, because I'm pretty sure with 50, she's at least got a fighting chance. All right, now let's just watch the race. The good thing about this is, do you see that it's easy to make changes? So now, consider this a minute about knowing to put the 50 there. She's still going at the same rate, but we're just giving her the head start because X represents where she is. So she's going to start at time 0, 50 miles out on the track. All right, here we go.
Tragic.
Yes, all right. They're off, and Ellen is in the lead, and Thomas is working to catch up, and I believe she got there first, right? Okay, all right. Now, let's go back, and let's look at some other ways to do this. All right, now, this time, I want to delete all this stuff where Ellen's got her advantage. Okay, now, I want you to look at this one for a minute. All right, I'm going to put in a parentheses here, and then the T, and I'm going to go minus, and I'm going to go 0.15. Okay, now, do you understand what he's going to do is for 0.115 of an hour, so 0.15 times 6. So we're going to give Ellen a 9-minute head start. I deliberately made small because I don't want Ellen to just romp. If I give her an hour head start, she's going to win. Okay, so now watch what the race looks like this time. Notice that Ellen will start at the starting line instead of a head start. All right, but, okay, and wow, that 0.15 went by fast there. All right, remember Ellen's the one at the top.
Thomas has got it.
All right, and so Thomas still won. Now, do you see though how if you're going to do a horizontal race, all you do is you set it up where people are going left to right, but do you understand that setting up the window is a big deal? And then the X equation is always in that form, distance equals rate times time. Okay? Now, there'll be a homework problem or two tonight where that's what you have to do. And that'll be one of the things you'll be responsible for on the test. Can I do a race where two guys go in the same direction? All right. Now, let me put this down for a second. Go back here. All right. Now, the other one here is, I'm just going to bring it out, but we're going to have two people going in opposite directions this time. Okay. So let me go here for a minute. All right. Are you familiar with the game Capture the Flag? All right. You know how people start on both ends and they run towards the middle, and whoever get the flag first gets the flag, right? Okay. So now, this time, let's set up a field that's 100 yards long. We're going to put the flag right here in the middle. All right, and we're going to have one person run this way to try to capture the flag, and we're going to have another person run this way. Okay? All right. Now, let's see. Melissa, let me have you run this time. All right. Melissa's going to run from left to right. Okay. So let's give Melissa some characteristics here. All right. We're gonna say that Melissa can run at 10.2 yards. Let's see. That's world class there. I'm going to back you down just a little bit from world class. I'm going to get you going 8.9 yards per second. That's still relatively fast. All right. Let's see. Sarah, let's have you race against her. All right. Now, I'm going to make you go 8.8. All right. So you're going to lose the first race, as you understand, and then we got to see how we can help you win. Okay. Now, let's come up with our equations here. So on Melissa, well, now, first of all, do you see what we want here is the flag is going to be positioned in a certain place, and we're not going to draw the flag as a flag. We're going to draw a vertical line right there. Okay? All right, and so I'll show you how to draw the vertical line in just a minute, but this is going to be Melissa. So for the y coordinate for both girls, let's let it be a 3. Okay, so Melissa's going to be y1. Let's see. I'll make this y2 and this one y3 because I want to draw this other line to start with. Okay, now for Melissa, since she's doing this 8.9 yards per second, that's just going to be 8.9 times t, no problem there. Okay, now over here, I'm going to do something wrong, so don't write it down. All right, if I wrote here 8.8 t, all right, I need to make it negative to make her go to the left. Okay, all right, that's a good point, Thomas. All right, now, if I make it negative, she'll go to the left, but if I put in just this, we will never see her on the screen. Why not? Where's she going to be at time 0? All right, 0, right? Where's she going to be at time 1? Where's she going to be at time 1? Just put a 1 in there. Negative 8.8. So she's going to be starting here and running that way, right? Okay, so what we need to do is we need to make her start over here, which is at 100. Okay, so when you have somebody running to the left, you need to give them a starting point. Okay, so they're starting at the right end, and then you put a minus in front of their rate like that. Okay, now that'll set up the race when people go in opposite directions. But it's a big deal about this 100 right here. That's an important thing. Okay, now I'm just going to write something down here. If you want to draw a vertical line, all right, for your x coordinate, you want to put where the line's going to be. So we want the line at 50 yards. Okay, so that's going to be 50. All right, and then for the Y, however tall your screen is, okay, what's our Y max? Anybody got the Y max? It's 6.2. All right, so right here, we're going to put our Y max and then just do 1 minus T. And I'm just going to tell you that what that does is that's going to make us start with a line at the top and draw down, okay? And the line will be drawn before the girls get to where that's at. Okay, now, I need to put all this in mine, and you need to put it in yours. So for this is going to be X1 and Y1 because I want the line to be getting drawn at the same time. Actually, it doesn't matter the numbers on these because it's simultaneous. So let's go back to here. Let's clear everything we've got here. All right, now I am going to put the line part in first just so we can just see it's there. And please understand that on this is something I'll explain better later when the line becomes a fence in a ballpark. Okay, now we've got 8.9 T for Melissa and running on lane 3. All right, and then right here we've got 100 minus 8.8 T, and she's running on lane 3 too. Now we need to set our window. All right, so let's see. If they're running like 8.8 yards per second, it's going to take them more than 5 seconds to go 50 yards, right? So let's make this into a 6 here, all right, with a step of 0.1. And we need to have this thing here be 100 for Y max. And let's let the scale be 10 this time. And that way, if you're interested, you can see where the 50 really is. All right, watch it on this one. And then if you don't mind doing it on yours, I found in the past that the people who learn are the people that put it in their calculator, because there's something about the memory process when you do something that's tactile with the thing in your brain that's better than just watching, all right, to cause you to remember it. All right, now here we go. All right, do you see how fast the lane went in there? Okay, now the bad news here was I did not put the arrows on them, so it's a little bit harder to tell who got there first because the race is over amazingly fast here. So let's go back here and get the arrow. All right, and we'll go down, and we're going to get the same thing. Right, okay, and we don't need that on the fence. All right, now that race got over in a hurry, right? All right, so one thing we can do to slow the race down a little bit is we could make the T-step smaller. So I'm going to put 0.05 just to make it last a little bit longer so I can explain. All right, now here we go. So you can, let me break that. I put it on the wrong thing. All right, I put this on the fence. I don't need it on the fence. Okay, now I do need it, let's see, right here in this place. Okay, now here we go. Oh my goodness, the girls are crawling. All right, let's put our 0.1 back in there. Okay, I don't know why it went so fast that first time, because it looked like it went really fast without the bubbles on.
Does it go slower with the circles?
It goes what? It goes slower with the circles. Okay. All right. Now, but you can see that they're going towards each other, right? All right. And Melissa she's coming here, ought to get there just a little bit faster. Boom, and then all of a sudden they're going to either hug or crash, depending on how you want to look at it. All right, any question about just doing that? Because you got to be able to get them coming from that. Okay, now we're just going to do one other thing with this. All right, other than speeding Sarah up, we can either give Sarah a head start. Okay. Now, if I wanted to give Sarah a head start here, so let's go down to Sarah's equation. What would I need to do to give her a little bit of a head start? Like if I wanted to give her a 5-yard head start.
Make it 95.
Yeah, make it 95. Okay. Do you see that all this, well, just 95 and delete that. All right. Do you see it just becomes applied common sense? All right. Now let's look at the race. We probably should have made the t-step 0.2 to speed it up a little bit here. I don't remember in the past it being this slow when we did this, but it's going to be close still, right? No. Okay. All right, so Sarah gets there first and then goes over and smacks her. Okay, on the other side. All right. Now, anyway, that's the first kind of motion that we can have. It's just where it's horizontal motion in some way. Okay, now, here's the key with horizontal motion. The y coordinate is always a constant. I don't know if you need to write that down or not, but if you're a person that thinks you'll forget, horizontal motion, y coordinate is a constant. All right, now, on the next slide, we're going to talk about simulating vertical motion and then particle motion. Okay, now, with vertical motion is a little bit of a dud. For example, this is what you're going to see in a second. We're going to have a ground level here. We're going to send something up in the air. It's going to go up. It's going to come right back down in the same place. All right? Now, that's about as exciting as watching paint dry, but there is a problem in the homework you got to do with it, so we're going to do that. Now, here's the deal. When you do vertical motion, the x-coordinate is a constant. Okay? Now, on this part right here, this is a formula that in physics you know as being this. It's 1/2 gt squared plus v sub 0 t plus h sub 0. Okay? Now, in physics, when you have this thing, g stands for the coefficient of gravity. All right, now, in Mr. Hasselberg's class, you guys measure in meters, and so you use 9.8 meters per second squared as the acceleration due to gravity. Okay? Now, in the way I'm looking at this, we have to have that as a negative because gravity is directed down. Okay? Because right here, notice we get a minus sign right here. Okay? Now, in our class, we talk about feet per second, and so the coefficient of gravity in feet per second squared is this, negative 32. All right, and so what's going to happen is every time we do something, this first term right here is going to wind up being negative 16 t squared. You need to get used to seeing that. That always means gravity's involved, and it's motion where we have to, we're dealing with a y coordinate. All right, now, v sub 0 is just instantaneous velocity. All right, any of you guys play baseball? All right, Davis, you did, right? All right, Nick does. Either one of you a pitcher. Okay, all right. Now, because you're a pitcher, I'm going to assume that you have a fairly good arm. But suppose that you're just here and you're going to just throw a baseball straight up in the air. Okay, all right. When it leaves your hand, it's going to be going at a certain rate in miles per hour or feet per second. We're going to measure it in feet per second. All right. So I'm going to say right now that we're going to use that v sub 0 for Nick right here as being, let's go 120 feet per second. Okay, now that's pretty fast. I don't know if somebody's throwing something straight up, they can throw it that hard or not. All right, but now just for a reference point, remember that 88 feet per second is equivalent to 60 miles an hour. That's a good fact to know. So 120 feet per second would be close to 85 or 90 miles an hour. All right, and that's really hurling if you're throwing it up. So, but anyway, we're going to make Nick into a great arm right here on this. Okay, so right here, if we were doing this, we would write in here the 120 T. All right, and then the H sub 0 is the height of the projectile when it's released. In other words, like when Nick releases this thing straight up, he's probably going to be releasing it above his head if he's throwing it up. And he might be coiled a little bit, but I dare say that the ball would be at least 6 feet above the ground when it's released, right? Okay, so I'm going to say that our H sub 0 here is going to be 6. Okay, now, when you do vertical motion, those are the only things you have to consider. There's going to be an initial velocity, there's going to be an initial height, and then we're going to always get negative 16t squared. Okay, so now, on the x on this thing, I'm going to just make x5. Okay, so let's watch Nick throw the ball up in the air. Okay, so let's clear out all our junk. Okay, now if we go back up here, we're going to get a 5, and then we need this equation that's negative 16t squared plus 120t plus 6. Okay, now go back up and go over and highlight it so it looks like a ball. Now, I'm going to do the one that's got the thing attached to it. You might want to do on yours just the ball. Go one more and just get the ball where you see it go up and come down. But I want to have this thing. Okay, now, the hardest part about vertical motion is to get your window set up right. Okay, so now I want to try to give you some concept about the window. So, right here. What we're going to do is we're going to go from 0 to 10 on X, and that's why I put this as a 5. That way it's right in the middle of the screen. Okay? Now, do you see that this is a parabola right here? If we were graphing it as a function, it would graph as a parabola. Now, the highest point on a parabola is the vertex. And remember when something was in the form ax squared plus bx plus c, that would give us, it was x equals negative b over 2a. Okay, so if we do negative 120 over negative 32, whatever that number is, that will be the time when this thing gets to its highest point. Okay, so somebody with your calculator out, what's 120 divided by this?
3.75.
All right, 3.75. Okay, Michael, have you got those in already?
Yes.
Okay, then I want you to go vars and then y vars, and then number 2, or whatever parametric is. I believe it's number 2.
Yes.
All right, and then go y1t. Just press that one. All right, and then put a parentheses and put 3.75. All right, and then just press enter. You close the parentheses, and it should give you the height that it goes to.
Oh, okay. I did it in y equals just then.
Oh, okay.
My bad.
All right, you're good. I'm going to do it here just so people can see it too. So it's vars, and then y vars, and then parametric, and then we want the y1, so that's a 2. Wait a minute.
231 though.
All right, I was doing that inside this function. All right, so I just screwed the function up. I got it. Let me go back and look at that. All right, but 231. All right, let's hold that for a minute. Let me just see if I actually got in to change it or not. It might not have put anything. If it put it, it puts it at the end. All right, it's not there. Okay. All right, now, from Michael's thing, we got 231 feet. Okay, now, so let's go to window. All right. Let's go down here to x min is 0, x max is 10. All right, and then for the scale here, we'll just let that be 1. And then for y min, we want 0. And for y max, let's put 300 because I want it to definitely be above the top of where it goes. And we'll put a scale here for like 50, just so we can see. All right, now, let's go back up and talk about the T min and T max for a minute. All right, this number 3.75 here tells us how long it took for the ball, once it left Nick's hand, to get up to the top. Now, it's going to take that same amount of time for it to get back down to how high Nick's hand was above the ground. Okay, so if we double that, that'd be 7.5, but the ball at that time would still be 6 feet above the ground. So if we would make this an 8, then this would be plenty big enough. So right here, we're going to change the 6 to an 8. Okay, now one or two of you will have trouble adjusting the T's. And so basically, if the projectile doesn't get all the way back down to the ground, just means your T interval's not big enough, just make it bigger. It's never bad to have a T interval that's definitely too big, because all it's going to do is it's just going to show it disappearing. Okay? All right, now let's look at this. Like I was telling you before, this is not something that looks super. All right, but we see it going up. So Nick's released it, it's going up, and gravity's taking over, so it's slowing down. All right, now notice that's about where that 231 would be, and now here it comes, and you'll see it speed up. And if Nick didn't get out of the way, pop him in the head. Okay? All right, now, any question about that? Sort of a dud with that part, but it's there. Okay, now, let's go back to that equation, and I want you to change that 5 to a 9 for a minute. All right, so what we're going to do here is we're going to get the look of that ball going up and down over on the right side of our screen. Okay, now, what I want us to do this time is I want us to look at this more like we would look at projectile motion. Okay, now on projectile motion, if the ball is thrown to the side, if I take the ball and I throw it in that direction there, then it's going to have a certain horizontal velocity and a certain vertical velocity. Tell you what, let me hold that for a minute. All right, because what I want us to do on this one, I just want us to see something else that the book does with it. So let me just explain it without telling you that part yet. Okay, right here. Would you go down to y sub 2 and would you just put a t? Okay, and then go down here to, that's x sub 2, I'm sorry. And then for y sub 2, I want you to go vars, y vars, 2, 2. In other words, that's the same equation. Okay, so what we're going to do here is we're going to see how high the ball is at a given time. So we're going to see a parabola look on the left, and then we're going to see the ball going straight up and down on the other one. Okay, now, I want us to come right here, and this time I'm going to go all the way over to where just it's the ball, but it's not connected, just to have a look. All right, watch it here and then watch it on yours. Okay, so you can see this is what's really happening, but this is just showing me how high the ball is at whatever time intervals happened so far. So it's just comparing the height to the time interval. Okay, now that doesn't look overly informative. By the way, those should hit the ground at perfectly the same time, so when you do simultaneous, it's plotting a point on one and then a point on the other, then a point on one, then a point on the other, and that's why it looks a little bit uneven there. Okay, now, anyway, for what that's worth, there is a homework problem tonight where they asked you to just do that. Okay, now, the thing that's interesting is projectile motion. All right? Now, we're going to do this problem. All right. Now, this is one where I got it printed on yours so you can see it. All right. We want a batter to hit a ball that's 3 feet off the ground, and the bat's going to come off the ball at an 18-degree angle with a horizontal with an initial velocity of 150 feet per second. And then we want to find out how far from home plate will the ball hit the ground. All right, that's the first thing. But we're going to find all of these things right here for a time here. Okay, so now we're going to let Davis be the batter this time. All right, so you need to be able to look at this. So if you need to be able to just hold back a page to see it, you need to be able to see this as I discuss what's going to go on here. All right. Now, I'll write what we need here so that you can be with me right here. All right. The x is equal to the cosine of theta times t. Okay. Now, notice right here that we are given the angle measurement in degrees. So that means that in this problem, we will need to go to degree mode. All right, so I'm not going to put my calculator up. You have to change yours to degree mode and then remind me to change mine. Okay, so now I want to give you an idea of what we're trying to draw here. Here is home plate. So we're going to put home plate at point 0 right here. All right, now eventually down here, we're going to get to a question that says, will the ball clear a 15-foot fence that's 400 feet from home plate? All right, so we're going to build a fence at 400 feet, and then we're going to go over here to 450 feet. In other words, we want to have some area behind the fence because we want to see if the ball gets over the fence or not. Okay, now here's the idea. The pitcher throws the ball, and it's 3 feet above the ground. So that's not quite belt high, but it's real close. And Davis, hopefully being the good hitter that he is, hope he's a good hitter, all right, hits the ball. All right, now there's horizontal right there. He hits it at an 18-degree angle with a horizontal. All right, and he hits it with a whole bunch of force here. Okay, and so now the ball's going to go on a parabolic arc. Now the question is just going to be, A, does it get to the fence? And then B, if once the fence is there, does it get over the fence? If it doesn't get over the fence, how high up on the fence does it hit? And we want to be able to answer all those kind of questions. Okay, so now what we need to do first is we need to get the horizontal position of the ball. All right, and so all we're doing is using this formula. And so, let's see, I left something out there. It was V sub 0 cosine theta times t. Okay, now something else, just because I can't stop trying to mingle some things here. Do you remember when we did vectors, the component form of a vector was its magnitude times the cosine of theta, and then its magnitude times the sine of theta? Those were the components of the vector. All right, that's what we're actually doing here. In other words, we're putting the horizontal component times t. So when Davis hits this ball at 150 feet per second, we don't have all of that velocity applied horizontally. It's going up, and so what we're really doing, all right, right here's horizontal, right here's vertical, and Davis hits that thing where his velocity vector is 150 feet per second, and the angle right here is 18 degrees. And so what we're going to do is we're going to get that horizontal component, which is this. And so that tells it the rate at which it's going across the field, horizontally. And then we're going to get the rate at which the ball is going up, because some of that impetus is causing the ball to go up. And then a majority of the impetus is causing it to go towards the fence. Okay, and so that's where this comes from. So right here, this initial velocity was 150. The angle was 18 degrees, and then we put the t there. Okay, now this 18 degrees is going to need to be in a parenthesis when we put it in the calculator. Now, the y-coordinate from the other page was negative 0.5 g. I believe that's the way we had it. T squared plus, all right, now, for the initial velocity here, instead of having V sub 0 like we did when it's vertical, we're going to get the vertical component of this. All right, so it's going to be the initial velocity times the sine of theta, and then the last thing, and there's a t here, and then the last thing's an h sub 0. That was like before. Okay, so right here, when we write ours, this was the formula. This is going to become right here, negative 16, and then a t squared. Now we're going to get here 150, because that was our initial velocity, and then sine of 18 t. The t is not in parentheses with that, and then we're going to get plus 3, because the ball was 3 feet above the ground. Okay, now all that I'm doing there is I'm up here, I'm identifying that this number is h sub 0, that this number here is theta, and that this number right here is v sub 0, and then I'm just plugging them into the formula. So that's just like, it is a formula from physics that we're applying, okay? All right, now let's put that part in our calculator. All right, so for me to see that and for you to see that, I'm gonna move this over. All right, we want to clear the junk that's here. Okay, so we need 150 cosine of 18, and then the t is outside that parentheses. All right, I'll do that as soon as I get this one in. Thank you. All right, now I want negative 16 t squared, all right, plus, and now I need that 150 sine of 18, and the t is outside that parentheses, plus 3, bless you. All right, now let me go to window and get that taken care of. All right, now on baseball problems, the ball is almost always out across the fence within 5 seconds. All right, but I'm gonna put a 6 here, and then if we ever see a ball just hanging in the air, it took longer than that. Okay, now we do have a cosine in this problem and a sine, but it's a cosine at a specific value. So leaving the t step as 0.1 is still good. Okay, now on this, let's see, wait, let me go to mode before I forget. I need to get to degrees. Okay, now let me go back up here to window. All right, so we want 0 to 6. Okay, now on this one, because of wording that's on down in the problem, we're talking about hitting it across the fence at 400 feet. So we want to put in 450 here. All right, a good scale would be 50, because that way we'd get a tick mark at 400 and at 450. And then for the y min, it's 0. And then for the y max, a baseball almost never goes as much as a third high to what it does out. Okay, and so I'm going to put here 150 feet, and probably we'll come back and change that to 100. I think the ball here only gets about 38 or 40 feet high, just from doing the problem from memory. All right, and so the scale on this, all right, the 50 will be fine. That part doesn't matter. Okay, now let me go back to y equals one more time. Okay, and let me just get us to where we have the thing connected. And now we can see the flight of the ball. Okay, now let's hit that for a minute, okay? All right, now let's go back, because you can tell the ball is not getting as high as 50 feet high. I want the ball to look like it's going higher. All right, so let's change the y max to down. Let's change it to 60. That'll give us a reasonably good look. Okay. Now, all right. But do you get the idea? He hits the ball. You see it going out, and right here's where 400 is, and you can tell it's over 400, right? Okay. Now, let me put this down, and let's start answering the questions. All right. A, how far from home plate will the ball hit the ground? Okay. Now, when the ball hits the ground, what's its y coordinate? All right, 0. Okay. Now, which one of these two things right here? Well, let's see. I don't know how to ask the question. I'm geared into just telling you the answer. If we would go back and graph this in function mode, all right, as opposed to parametric mode, we could get where it hits the ground if we make a little bit of adjustment. Now, the reason for doing this one, all right, I didn't look closely at what the A part was, or I would have had us do this part first. But let's go back here for a minute. All right. go back to mode for a minute and go to function. Keep it in degree, but go to function. All right, now the reason for this is, if I put this equation in, so negative 16x squared plus 150 cosine 18, and the x outside the parentheses plus, let's see, wait, that was it on that one. Delete right there. All right. No, I'm sorry. My brain just malfunctioned completely. Did I put in the negative 16? Yeah, I did. Okay. The x is not squared here, is it? Can you tell if I squared that? Let me second insert square it. Okay, all right, that's what I'm looking for. All right. My brain jumped ahead of where it was supposed to be. Oh, I'm sorry. Thank you. All right, sine, and then plus 3. Okay, now on window, because we're in this mode, everything's taking on a different thing. The x now becomes the time, right? So we just need, for right now, 0 to 5. All right, and then, well, let's see, let me make that 6, because that's what we had. Wait, 0 to 6. 0, 6. All right, and the x scale here can just be 1 for this. All right, now for my y min, I want my y min to be negative 25. All right, because I want to have something down below the ground. Okay, all right, and now my y max can be 60. That's okay. All right, now look at this. You'll see it going up. You'll see it coming down. All right, now what we need to do here is we need to calculate this value. All right, and the reason that we went back to this mode is we can get the t value that, or what will be the t value for us here that causes this to happen. So we want to go second calc 0. Okay, now we want to get to the left of where it crossed, and I happen to be real close there, so I'm going to go there. We want to get to the right of where it's 0, which will be there, and then we don't guess, we just get this number. All right, so now we want to save that x value. Okay, so go second quit, and then go type an x and press enter. All right, so we see that we have it. Now go store alpha A. All right, and then press enter, and it gives you that number. Okay, now let's go back to mode and change back. Well, let's see. Before we do that, let me explain something right here. All right, if I want to find out how far down this direction we are, do you see it should be the x coordinate? It's the x value here at that t, at the t value we just got there. That'll tell us how far this way we went. Okay, and so if we evaluate x sub 1 at that value that we just saved, we'll get this. So let me go second quit. The easiest way to get to this is go vars and then y vars. Now we're looking for parametric. All right, go ahead. This is the worst place we could be in this problem. Go.
Fire would be out.